Well, good afternoon, everyone. Welcome and thanks for joining us today for this educational webinar. I am Neil Michael with Arm & Hammer Animal and Food Production, and I'll be your host today for a very exciting subject, using new technologies to manage immune response for improved health and performance. But before we begin, let me do a little bit of housekeeping. I would tell everybody that's on, of course, to please mute your phone, your computer, whatever you're logged in with, to minimize any distractions. Secondly, this webinar will be recorded, and we will make that available with a follow-up link in a few days that will be posted to YouTube, but we will follow up with a link to everybody that's registered here and online today. Thirdly, there are CE credits available for this webinar presentation, and when we're all done, I would have you just contact your Arm & Hammer account manager, technical service, for that application for those CE credits. And lastly, any questions that you have during the session today, please enter those into the chat session, and my colleague, John Schmidt, will be monitoring those, and when we're all done, we'll get through as many of those questions as we can, and those questions will be moderated by John anonymously. So go ahead and enter them into the chat session, and the only person that will be able to see those would be John. So that is the housekeeping. And with that, it is my pleasure to introduce our guest speaker, colleague, friend, Dr. Chris Chase from SDSU, professor in the Veterinary and Biomedical Department. And with that, thank you, Chris, and the screen is yours.
And thank you, Neil, for the introduction. And today we're going to talk about maintain a healthy balance as it relates to the immune system. And this is really an issue or I think a problem or a area that's really emerged in terms of understanding, particularly how immunity and innate immunity behaves, and the idea that we usually think of the immune system as something that we want to stimulate and that we're protecting the animal. But I think one of the things that's really come out in the last few years is the fact that the job of the immune system really is to try to maintain a balance. It's trying to allow microorganisms to do their thing, and at the same time maintain health. So that's a kind of a little bit different way than looking at. I think that in the past we just thought, well, the immune system's job is to be on the defensive predominantly and to go from there. So let's go from there. So I just want to give some credit to the some of the slides that I'm going to use today, and particularly I've got slides I've used from Dr. Kubi's book, and then from a book called Immunobiology. You're going to see a few movies today that are actually from that book, and then also from David Topham. So I want to begin then with this slide to again China, whose job was to keep things separated, and not the idea, in fact, that this is actually a very dynamic area. We'll talk about that today in terms of there's a number of things continually going on, because it turns out that this barrier and those epithelial cells that make up of it are actually the largest part of the immune system. So those cells aren't just there for secretion, not just there for absorption, but in fact they are there to actually regulate the immune system, and they do that by signals that they get from the immune system and then signals that they actually get from the lumen, whether we're talking about the respiratory tract or the GI tract, and predominantly today we're going to be talking about the GI tract. And then typically we would then think about, well, somehow that barrier got breached, that would then turn on innate immunity. And innate immunity certainly isn't that what I kind of like to think of sort of the smoke alarm business. Its job is to sense if anything's kind of gone wrong, and then being able to go ahead and recruit the other cells of the immune system to come in. So typically, innate immunity will pick up that something's occurred, and it uses predominantly, as you can see in this diagram, inflammation as its messenger to bring things in. And we know that, again, when it comes to innate immunity, there are both humoral things like cytokines, interferons, and that are involved with that, and then cells like neutrophils and macrophages that are very important parts of that. And particularly those cells, particularly the macrophage, is one of the cells that's really responsible for producing these inflammatory cytokines to get that immune system sort of geared up to go. And we know then that the last thing that happens in terms of this cascade is adaptive immunity. And again, typically when we're thinking about vaccines, that's the endpoint that we want to get to. Or one of the things that we're talking about even now with COVID-19 is the fact that, well, we're going to measure antibody and know that people have been, one, exposed and hopefully two, protected. And we know, again, the vaccines, what we're after is to protect those animals, and we know that those animals will have memory. So unlike innate immunity, which doesn't have memory, its job is like a smoke alarm. Wherever the smoke comes from, it doesn't care. But the acquired immune system has a very specific role in terms of how it responds to specific antigens. So again, you're going to have antibodies that are specific, say, for BBD, or antibodies that are specific for IVR, and the same thing with T cells as well. So, and as you can see from this diagram, these two systems work together. So if we don't have a good innate immune response, we're not going to have a good adaptive immune response, and vice versa. That after you've got a good adaptive response, they're going to interact with innate immunity as well and help, in some cases, to dampen it, and sometimes to increase it. So really to think about this, as I said from the start, the idea that this is more of kind of a balancing act, that we're going to, and we'll talk in a minute about this concept of homeostasis. But again, we want enough of that innate immune system to prevent and control disease. But again, one of the things that we've learned, and again, using COVID-19 as an example, is that what we're seeing where the people that are really having difficulty with this disease is that the immune system tends to overreact, and then we get immune pathology. And again, we know if there's not enough, and again, we think about that as sort of as immune suppression, not enough of a response, then the pathogen wins. And again, this immune response needs to maintain homeostasis. So that's what you see, this balance. And a term that I like to use that sort of describes this relationship about either too much or not enough is a term immune dysfunction. So again, sometimes the immune system over-responds, sometimes it under-responds, and we'll talk about that a little bit later. One of the ways that I like to think about just how the body has to react, and again, this is back to that idea of homeostasis, is that if you look at this PVC pipe that I've got here, and if you think about the inner surface of that PVC pipe being the digestive system, and again, that digestive system is going to have all the commensal organisms that are present in the intestinal tract. We know that's a huge number of organisms. Then on the outside, and on the skin of that animal, there's a microbiome that's on our skin, in our respiratory tract that's on the outside. And again, that too, the immune system has to deal with that. And that leaves us with just the PVC pipe itself, to be that body whose job it is then to sort of hold that balance or that homeostasis, realizing that some of the signals that it's getting from those microorganisms are very beneficial and are necessary for immune function, and then trying to figure out which ones aren't. So that's, again, that whole idea of trying to maintain homeostasis. So again, so if we define homeostasis, again, it's the process by which a calf or a cow maintains a stable, healthy internal environment. And again, the immune system, its major job is to maintain homeostasis. And again, it's up to the immune system then to sort of sort out the good guys and the bad guys. And we know that if they're the harmful or invasive entities, then we're talking about things like particularly pathogens that we're again trying to prevent in terms of the effect that they may have. Oops. Yeah. So this gives us the idea that, and again, we talked about that PVC pipe, but now think about it in terms of the calf. So the calf itself has got well over 1 billion cells, or several billion cells that it has. Each of those are expressing genes, and of course that's also involved with the immune system. So you've got all those cells doing their thing to try to maintain that calf, and maintain that calf in terms of being healthy, in terms of growth and those kind of things. And then on the other side of the fence, literally in the lumen of the gut or in the respiratory tract or in the skin, we have these what we call symbiotic microbes or commensal organisms, of which we have, they outnumber the number of cells in the body by anywhere from 100 to 10,000, depending on what organism that we're looking at, and being able to sort out that. So now we have what we call the microbial metabiome. And so those two things have to work together. So the part of the immune system is to try to fine tune those as much as we can, so that animal can have maximum productivity by using really what's going on in its body, along with what cues that it can get from that microbiome. And again, so we want to do that to get optimal fitness in terms of the growth and performance of that animal. Now, we know then that one of the major players, and again, I just mentioned to you this earlier, but it's the idea that that barrier isn't just a static wall, but in fact, it's a immunological organ whose job is actually to do really two things that I hope I will leave you with today. The first thing is actually to maintain that barrier. And again, that barrier is dynamic, it's literally fluid in terms of what it does. But what I wanted to describe to you here is really four important components that I want to talk about in terms of this barrier. So you can see the first thing I want to talk about is actually the actual production of mucus itself. So here you see this goblet cell, and its job is to produce mucus. And that mucus is a very important matrix to be able to hold antibodies, to be a physical barrier, almost like a filter in terms of that. It's also important in terms of some of the commensal organisms need that structure to grow in. So that mucus is protection. It's a material to hold other antimicrobial materials in, and it's also a matrix to allow commensal organisms to grow. So mucus is really very essential in terms of the maintenance of our barrier, and is part of what I'm going to refer to as the kill zone. The second thing I want to point out there that you see as with the abbreviations AMP, which stands for antimicrobial peptides. So what those are the body's natural, for lack of a better word, antibiotics that the body produces that will kill, in particular, bacteria. There's some that are also directed against viruses, but they're directed for the most part against bacteria. And again, their job is to kill bacteria that are seen to be particularly pathogens. Again, and they are produced by these cells, and you can see it literally by any of the cells of the intestinal tract. In mice and humans, there's just one type of cell, but in ruminants and swine, we actually know that pretty much any of these cells can produce this antimicrobial peptide. So that's the second component. The third component is actually not produced by these cells, but is IgA. Okay, and so if you look down here, you'll see here's the IgA. It's actually produced by the adaptive immune system, by B cells, but its transport is totally dependent on these epithelial cells. So here you see the receptor, whose job is then to internalize that, and then to transport it across the barrier and then put it on the surface. So then we have particularly IgA, which again is just going to be specific for microorganisms, and again is an important part of that kill zone. So the three components of the kill zone then are the mucus, the antimicrobial peptides, and then the IgA. The fourth component I want to talk about in terms of that's important just to maintain this barrier is something called tight junctions. And it turns out these tight junctions are also immune regulated. It turns out that the intestinal tract and the respiratory tract in general always want to be anti-inflammatory, because if you think about if they were reacting to things all the time, that's all they would do, because we have in that lumen, we have bacteria that are continually out there, so they have to be able to sort that out, and they do that by predominantly being anti-inflammatory. And these tight junctions then are proteins that knit these cells together and hold them together in such a way that bacteria typically can't get through there, and other metabolites and things that are in the diet could actually come across that barrier. So that tight junction is essential for that. But we know that if we have inflammation, and particularly from something called tumor necrosis factor, that what that causes, it causes those fingers you see in these tight junctions to relax, And then we end up having these cells separating, and we get leaky gut. And that's immune regulated. So even though the proteins are structured, in fact, they are immune regulated. So those four components together really are important, and they're dynamic. And we'll talk about how they're regulated as we go along here. All the things that we just talked about are regulated over time and by different components. So one of those that we know regulates that is actually the commensal bacteria and some of the metabolites that they produce. In particular, in this example, I'm going to talk about short-chain fatty acids and butyrate. Okay, so typically we think of those from a nutritional standpoint as being fatty acids that are volatile fatty acids that are important for nutrition, and if we're talking about lactating cows for butterfat and those things, but we know now that in fact they are an immune message. Okay, and so what you see in the upper part of this is you see commensal bacteria. One of the things they can do is produce these short-chain fatty acids. The short-chain fatty acids then can have a direct effect on these epithelial cells. So that's what you're seeing here, where these epithelial cells are stimulated, and they then produce another hormone. And I'm sorry to give you kind of all the immunologist shorthand here, but something called transforming growth factor beta, which is anti-inflammatory. Okay, and then that in turn regulates the cellular innate immune system and also the adaptive immune system to not over-respond. So it's to be anti-inflammatory, and that's what they're showing here. So these short-chain fatty acids produced by those epithelial cells will actually then cause the immune system to be what we call regulated, and that's what you see at the bottom here, that where it says a Treg cell. So that's a cell then whose job is to regulate and say, don't over-respond to that. That's something that's natural and normal. Don't over-respond to it. And the other thing that it does is that these cells also produce something called IL-10. And IL-10 is something that really turns on the production of IgA, and that's what you see here. So they really, this regulation does two things. One is it keeps an inflammatory response from occurring at too high of a level, and the second thing it does is it increases the production of IgA. At the top part of this figure, you can see butyrate itself, and that's what you see. This is showing is that butyrate can be absorbed directly across the mucosa and have a direct effect on these same cells. So you see the T cells and the dendritic cells. So again, regulating them. So again, say you respond to this, don't over-respond to that with a regulatory cell, and then also turning on IgA. And again, as I said, the thing about maintaining tight junctions and maintaining the best function of both the respiratory tract and the GI tract is maintaining anti-inflammatory state in those barriers. All right, so let's talk about what are things that then might influence in terms of how the immune system reacts. And the big one there is stress. And you can see I have a very broad definition of stress. It's anything that can reduce the immune response capability, which means could either be too much or not enough. Okay, and so again, that idea of trying to maintain that homeostasis. And we know that anytime that we're in intensive production, that is an increased stress, because we've got more density, we've got other things in terms of housing, the other things that occur, so that typically that is going to be more stressful than a more extensive. So if we're talking about being in a pasture in terms of how those animals are going to respond. And these are just a number of stressors that are out there, and you can see these are all things that we're all aware of. Everything from obviously other diseases, other animals, the age of the animal, whether they've been transported, commingled, and then things that probably you don't think a lot about, like vaccination. But vaccination, depending on what you're using, it can be a major stressor in terms of turning on inflammatory responses as well. So there's lots of things that animals do, and lots of things that we do to animals that really fall into that idea of being a stressor. And we know then that if you put animals under stress, that there's an effect on the bacteria that are in the gut. So if I have an animal that is off feed, that's a stressor, okay, or it's dehydrated, that it will change that microbiome. Or if I have given that animal oral antibiotics, I'm going to change that microbiome. So normally that microbiome is interacting with the epithelium, and that's what you see here. So the purple guys are the good guys. They're interacting, they're causing that kill zone to be nice and thick. So there you see mucus, there you see the green dots, the antimicrobial peptides, IgA, and you can see there's some pathogens there, but they don't get a chance to come in. And when it does occur, there's not much of an inflammatory response. Now, if I have a stressor, and again, so imagine it's off feed, I've changed diets and those things, and that microbiome gets depleted. Now what you see is now that kill zone changes dramatically. Now I don't have that kill zone there, and I also don't have the commensals that are sending the signals to help maintain that barrier. And so now I'm in a better, more likely shape that I'm going to actually have that gut become inflamed and maybe having to deal with issues like leaky gut. We also know, so I just showed you that in the intestinal tract, what can happen, but we know this is an example looking at the respiratory tract. And what you see here is that, in fact, if we're doing things like dehorning or castrating animals or having some kind of abrupt weaning, will have an effect on the production of cortisol. And then if we have a viral infection on top of that, that cortisol and those things will increase the chance that these microbiome changes. So instead of it being in equilibrium, we get this what called dysbiosis. So instead of having that nice thick layer that we saw on that previous slide, that ends up being thin like we saw on the right-hand side of that slide. So the thing though about respiratory disease is that a lot of, especially the bacteria, they're normal inhabitants already of the upper respiratory tract. Okay, so now we've changed the balance. So you'd have, there'd be Mannheimia up here, there'd be Maltosida, Mycoplasma bolus. But now if we change the colonization that we have, now what happens? We have more of the bad guys up here in the upper respiratory tract. And then if we have other stressors, so again, a lot of things that you just saw on that list, and heat stress being another one. Now that changes how we can clear the bacteria. It makes it easier for bacteria to get down to the lung. And now what do we see? We see bacterial pneumonia. But again, what it started out with is with a dysfunction that occurred, particularly in this case with the mucosa, and the fact that the bacteria, and then allowing the Mannheimia and the other bacteria that colonize that to overgrow, and now it makes it easier for that animal to get bacterial pneumonia and shipping fever. All right, so let's talk a little bit more specifically about these cells and what they do, and again, why we want to limit them. So again, as I already told you about innate immunity, its big job is to, like I said, I like to think about it as being like the smoke alarm to track. So first to detect and then to track other troops in. And as I already said, it's absolutely essential for the vaccine response. And again, so one of the things that it does is that, especially neutrophils and macrophages, that they actually will take up bacteria and they will kill them. And again, that's a huge part of what they do. And again, we need that to help protect the animal. The thing is, we need to try to regulate that. So again, if you look at macrophages, and again, here you see this is the cell right here, and it's getting stimulated. And what they do is they produce these inflammatory cytokines, okay? And when they're stimulated, and those inflammatory cytokines, again, essential for a vaccine response. So imagine I'm given a vaccine, I give that as an injection. One of the things it does is they produce that inflammatory cytokines, and I see that little bit of swelling that occurs there. That's sort of that local response that we see. The second thing that inflammation does that's essential for a vaccine response is that it affects the regional lymph nodes, and it causes cells to move into those lymph nodes where they're just downstream from where the inflammation is. So again, increasing the chances that when my vaccine antigen gets to the lymph node, that the T cells and B cells that are for that antigen will get a chance to get together, and they'll have a really good vaccine response. So that regional effect is really important as well. And then the other thing that happens is that systemic effect. So the systemic effect then is an effect that we'll talk about here in a second. That is also one that we see when we vaccinate sometimes. Again, that's an effect that typically, we see that as a side effect, but it just tells us that the immune system has been turned on in terms of inflammation. So locally, what we would normally expect these bacteria or these to do would be that, and this is a neutrophil, and I call this sort of the pastoral neutrophil, because what you're going to see here is you're going to see how this neutrophil actually will kill, in this case, Staph aureus. So we've got one cell here that's surrounded by red blood cells, and there's the Staph aureus. And what you'll see then is you'll see this bacteria or this neutrophil begin to chase after it. And there it goes, and it will continue. And it looks like the bacteria is running away from it, but in fact, that's what's called Brownian movement. But the neutrophil is attracted to that staph, so you can see that. So what it'll do here is it'll finally get that staph kind of rounded up, and you'll see it engulf it, and then we'll see that actually that it's going to be killed. So here you see it come up, and it'll surround it, and it'll take it up, and it'll kill it. And that again, that's the nice reaction. And typically after that happens, what we'd like to think happens is that those neutrophils then would just sort of round up and they would die. And when they do that, they go under something called apoptosis. But we know under stress that can change, and I'll show you that in a movie in a second. But we know then again that stress affects how those cells will move, and it also affects what happens after they get done doing their job in terms of actually eating the bacteria. And another thing we know is that particularly modified live BBD vaccines actually will cause those cells to be inhibited for even a week or two the first time you give it in terms of how well those neutrophils can actually perform. So here's another thing to, again, to illustrate to you about stress, and again, in inflammation. So again, we're looking at the flow of white blood cells, and here you see in the lower part here, that's actually the vein, and you can see the white blood cells are rolling along, and what you'll see is this inflammation is occurring where the little red dots are coming up. And what that'll do is it'll make that vessel get sticky, and what that does is then that causes those cells to get attracted across. And you saw that previously in the slide with the macrophage showing you that those cells are brought across, and that's how it does this. And the same thing happens in the lymph node. At the top, the cells that are speeding through, that's an arteriole, and arterioles don't have the stickiness to them, and they're thicker walls, so the cells don't stick to them. So they only come into the tissue as you see in the venule, and that's what you see at the bottom of this. What you're going to see in just a minute is what happened actually in a mouse. So they're actually going to take this little cartoon, and now they're going to superimpose it in a mouse, and you can actually see the movement that you see here that's streaming through here are red blood cells. So they're moving really fast, but the white blood cells will actually stick, and as they stick, you'll see them then they can flatten out. Okay, and you see that right here where they're flattening out, and then as they flatten out, they'll move down in and then actually move into the tissue, and you'll see that in just a moment. But again, you can see the red blood cells going through, and the white blood cells, they stick, and again, because there's inflammation there, you can see that. Now, what you're going to see in just, because there's when you see flattening out, what we call margination, and then in the lower part of the panel, they're going to show you 3 cells there that have actually already gone into the tissue. And now they put the clamp on there, and now you can see it's changed the dynamics dramatically, and so you can actually see the red blood cells. And I like this because you can imagine, and it's a little dramatization, but if this is an animal that was dehydrated, we know that dehydration has a big effect on how well the animal's immune response is going to work. And you can see that when you actually slow the blood down. So if you imagine dehydration, it really changes what will happen. So again, and we know that stress will also affect about how well these cells will be able to attach. All right, so as I mentioned to you before, this whole idea that inflammation is important in terms of that vaccine response, and then we have a local effect, a regional effect, and this is looking at the systemic effect. And this is where we end up seeing things both from a vaccine sort of side effect standpoint, but also from an animal performance standpoint. So that local inflammation, and here are the same cytokines that we saw before. So when it comes to a vaccine response, what's important is these cytokines cause the bone marrow then to produce more white blood cells, and that's essential for vaccine response, and it's also essential for infections. And that's something that we can't see other than when we measure, obviously, white blood cells in the blood. But then when we look at the other effects that they can have, and again, if you think from a vaccine standpoint, when you give a vaccine, and sometimes you see those calves be listless, or they go off feed, or they'll have the sweats. That's due to the effect that these cytokines have on the brain, because they affect the appetite center, the attitude center, and also the febrile response. Now, another effect, though, that we understand that these cytokines can have is on the liver. Okay, and there they cause the production of acute phase proteins, and again, that's important for the innate immune response. But on the other hand, the continual production of those, or the stimulation of those, is going to change the liver from being a metabolism machine to being an immune organ. And the interesting thing about the liver is that it is the first immune organ. So when it sees inflammation, it kind of wants to make that switch. And when it does that, okay, it helps in terms of the infection, but the problem with that is it limits then the efficiency of that animal. We'll talk about that in a subsequent slide. So this is the point then where we turn on inflammation, and can we have too much of a good thing? And this is a paper from a few years back that was in Nature. But what I like about it is that we've always thought about infectious disease and their effect is all about the pathogen. And here you can see the disease is as much about the host as the infectious agent. And the focus on the microbe is hindering research for treatments. And we're seeing actually that, again, if I use the COVID-19 example. So again, I think all of us understand this, is that if we don't have enough of a good thing, so in this case, the immune response takes a dip. We have we commingle calves. There's they've been introduced to BRSV or whatever for the first time, and now we see disease. But I would contend probably what happens more times than not, especially if animals are under stress, is that they've already got that inflammatory response has already been pushed up, and then now we come along either with an infection or additional stressor, and now we have too much of a good thing, and that can result in an immunopathology. And again, back to that concept of trying to maintain homeostasis, and it results in a cytokine storm. And that might be a term that you have heard, again, as people have talked about COVID-19, that's what we see in people, this idea that all of a sudden you got a huge pro-inflammatory response. And we know, again, that viruses like IBR and BVD are actually good at turning these on. And what we can see with just turning on these cytokines is actually high temps. So this is not from the infectious agent itself, but from the immune system turning on a febrile response. And then we can actually see the lungs themselves get injury from the excess cytokines themselves. And that's what we're seeing, again, with people that with COVID-19, and we also see it with respiratory disease. We can see it with respiratory disease in calves as well, that these cytokines will actually cause airway changes and those kind of things. So we actually see disease. And one of my sort of favorite things is sometimes, particularly we'll see this in fresh heifers, where we'll see that there's there's a febrile response, and people know that there's a respiratory thing, so they immediately assume it's got to be some kind of respiratory disease. So one of the things that we've done is go in there and vaccinate them with like an intranasal vaccine for BRSV, thinking, well, it's got to be infectious because they got a fever, when in fact it may be all physiological. And so Barry Bradford, who's now at Michigan State, has actually done work where he's actually used aspirin in transition animals and shown that indeed that they had less mastitis, less metritis, less respiratory disease when he actually managed the inflammation rather than trying to quote unquote manage the microorganism. And if you think about that, the macrophages, again, they're the immune system sort of eyes, again, first responder. We've talked about that already with innate immunity. And then under stress, what happens? They become more activated. And that's what's showing the difference here between the left panel and the right panel, is that now that you can see those macrophages are armed with more receptors on themselves to really respond. And so one of the things that they do in the presence of gram-negative bacteria is they begin to produce more of these inflammatory cytokines, which in particular recruits neutrophils. And then the problem that we have, and again, remember in the lung, there's lots of macrophages. So if the lung it becomes inflamed, we recruit a lot of neutrophils. The problem with neutrophils is once they go into tissue, they have a very short half-life. They don't come back out again. So macrophages can, lymphocytes can, but these cells, once they go in, and they're kind of on a 6-hour leash in terms of time, and then at the end of 6 hours, they're going to die. And we hope what they'll do is undergo apoptosis and shrink up and disappear. But when animals are dealing particularly with inflammation, what you see is actually something quite different. And so I'll show you that in this little movie here. So this is a movie. These are neutrophils. So before I showed you, this is obviously a different magnification than the last movie I showed you. What we're going to do is we're going to watch one of these neutrophils here and watch what happens. And they're dealing here with it's actually with a fungal element. But if you watch this one, it's on sort of on about 9 o'clock on the picture, that you'll see it kind of starts to shrink up. But then instead of shrinking up and disappearing, which is what we want to, you see it begin to actually expand. And then what it does is it does something called net formation, which means it releases everything. And you just saw that it blows up and releases all those cytokines into the environment, which kills the microorganism, but it also causes collateral damage. And that you can see that as well in this little cartoon here, where you can see that in fact these neutrophils, when they get into tissue, they can actually cause that tissue to undergo clotting, fibrin formation, and we end up with lungs then that look like this. And so here's a lung, and from a kind of a classic, day before calf is normal, the next day open it, you find it dead in the lot, open it up, and here's the lungs, and you can see that they're covered with fibrin. And it turns out, what is that? Those are acute-phase proteins that are produced by the liver. So again, it's an overreaction of the immune system. And again, I mentioned to you this idea before about how inflammation can affect particularly tight junctions, and that's shown here with the idea that, again, you see macrophages, that green cell right here, and see that they're producing this inflammatory cytokine that causes these tight junctions to break down, releasing these materials then into the tissue space. So now you have more inflammation, and it just begins to feed on itself, and you begin to see leaky gut. So again, if we can block that, that's really important. And we know, again, that leaky gut can be due to a number of things, and you can see those listed here from transition, heat stress, weaning, physiological stress, all affecting leaky gut. And leaky gut results in inflammation. And even though it's in the digestive tract, that inflammation can actually affect the respiratory tract. It can affect in a cow in terms of mastitis. So inflammation in one area, and then you see that where it says distant inflammation, can then affect another part of the body. And again, it goes back to the concept of cytokine storm. And this is just showing you lungs with that acute respiratory disease that we can see, just that's a result of the cytokines themselves. So this is from a human lung, and showing you this is kind of your acute pneumonia. These are all neutrophils in here. And this is more of a chronic form. So the people that they have to keep on ventilators end up with forms that look more like that. So again, it's a big issue that we see with COVID-19. And as I said, when you turn inflammation on and you affect the liver, you end up affecting a number of things. So we talked about sickness behavior, feed intake, and sweats, but then we're talking about then what does that mean to the productivity of the animal? So feed conversion, gain, increase in bovine respiratory disease, and in the cow, decreased milk production, increased mastitis, and increased vitritis. So those are all things that we see when we have too much inflammation. So again, the key here is, again, trying to get that balance, so they got just enough to prevent disease, but not too much. So too much immunity, so we have pathology, not too little, and again, trying to maintain homeostasis. So let's just talk real quickly then about how we think probiotics and prebiotics fit into the picture of what we just talked about. So we really talked about two things when it comes to that epithelium. One is strengthening that kill zone. Okay, so that's what you see in the first part. And the second thing is modulating that inflammation, so we can minimize that. Remember, I told you we're concerned about making sure that that gut is anti-inflammatory. So again, trying to minimize that is important. And we think those are two important mechanisms that are involved in terms of nutraceuticals like prebiotics and probiotics. So in this slide, and again, you're seeing the kill zone and the idea that, again, that we've got these probiotics stimulating, again, antimicrobial peptides, also helping in terms of increasing IgA production, and at the same time with this TGF-beta helping to maintain tight junctions and keep inflammation down. So again, those two things together helping to keep that barrier even in better shape. So, and again, improving the kill zone is really important, but again, also modulating that immune system is really important as well. And another thing I want to leave you with is the idea, again, that when it comes to the microflora and those commensal organisms, that when we talk about nutrition, we're not just feeding the animal. Because remember, I showed you that, okay, here's the cells of the animal, and here's the cells that are in the gut itself that we're supporting both of those. So we've got to think about that when we're doing that. So when we have diet changes, or we have animals that are off feed for a while, it's going to have a big effect on the microbiome, and that is important in terms of immune regulation and production of vitamins. And we even know they've shown this in people that are obese, that you can actually take their microbiome and put it into two similar mice, and the person that's obese, that will actually make that mouse obese. So these microbiomes are also involved in terms of efficiency as well. So the takeaways then is, when it comes to the innate immune system, that we want to try to avoid as much sort of additive inflammation as we can. Okay, so vaccination, if we're using gram negatives, we want to be careful about that. Surgical procedures add to stress, and also in terms of inflammatory responses. If we start on too hot of a ration, that can also have an effect on the inflammatory response. And I've mentioned to you already, but hydration is really important. And again, this microbiome needs to be managed and not upset. And again, it's so important to modulate this immune response. And that really leaves us, and you're going to hear that from Neil, in terms of where the strategic use of pre and probiotics are. And really, we like to say, ideally be prior or during times of stress. And then, but the question I ask you is, when do you not see stress? So all the things that we talked about are stressors. So you just kind of need to look at that. And I kind of put that under the term of risk mitigation. So anyway, that's what I wanted to cover before Neil takes over. So with that, I will turn it over to Neil.
Well, thanks, Chris. So I think what you've given us here is a whole lot of information to really think about disease differently, to really think about not just the way we've thought in the past of just focusing on a pathogen, find the pathogen, kill the pathogen, or bind the toxin. I think this gives us really a whole new opportunity to use new technologies to really manage the immune response, like you've just talked. So, that's why we do research. And as we continue to do research, we've been able to improve our ability to really isolate compounds that we've had for a long time, but isolate them in a form that is so they're much more bioactive, so they can manage things like Dr. Chase has just shown us here, and I will show you examples. And really also, as we do research, to really look at targeted microbial solutions. In this day and age, looking for non-antibiotic, all-natural targeted solutions. And I'll show you examples of those. So 2 specific technologies that we work with at Arm & Hammer that I'm going to show you examples of would be two examples I'm going to show you here are refined functional carbohydrates. We're going to call those RFCs from now on in the examples, and we can use those bioactive functional carbohydrates, the MOS, the mannose, the beta-glucans, to not only the way we've used them traditionally, but actually improve barrier function, like Dr. Chase has just talked about, and gut integrity. Of course, those RFCs are in our product Cellular. The second technology I'm going to show you an example of an immune impact is really our bacillus species. That's using really one bacteria to fight another bacteria, a targeted microbial technology. But we also know from our research that we can do many more things with these bacillus species than just attack different bacteria. We can also impact digestibility, our research is showing. And because we're talking about immune function today, I'm going to show you an example of an impact on gut integrity. That would be in the Certillus product, of course, our bacillus. Any of you who have worked with us working with this Certillus on the Clostridial, both toxigenic and non-toxigenic. So an example here of RFCs. I said we've had MOS, we've had mannose for years. What we are now able to do with our manufacturing process is actually isolate those RFCs so they're much more bioactive. They're much more effective at agglutinating this family of bacteria, the E. coli, the Salmonellas, the Klebsiellas. Okay, and we do that because this family of bacteria have a type 1 pili that is actually mannose dependent. They use those pili that are mannose dependent to bind to the intestinal wall. We use our RFCs that are highly bioactive to stop them before they get through that killing zone that we just looked at, to actually agglutinate them and keep that barrier intact. But again, what I'm going to show you are immune impacts that it's much bigger than just the bug. I think we need to think about these as pieces to the puzzle and really impacting the whole immune system. The second example here that I mentioned was our bacillus. We traditionally use bacillus, and we talk about using a bacillus targeted against Clostridia, both toxigenic and non-toxigenic. But Dr. Chase talked a lot about tight junctions and the leaky gut and the importance of those tight junctions between the enterocytes. And let me get here a pointer. This is just a depiction of two enterocytes and held together with tight junctions that he's been talking about. Specifically, we're going to look at three tight junction proteins here: occludin, ZO1, and JAM, that you can see those here that actually hold those enterocytes together. Well, this work by Lilio and their group at Beltsville, Maryland, the USDA, in 2017, they actually looked at these tight junctions and looked at gene expression with different treatments in these animals, and this was actually using poultry, but poultry upregulation of tight junctions. So what they did was look at gene expression with a control, with a BMD, as far as used as improved feed efficiency. And then they looked at three different bacillus strains or combinations of bacillus strains here. And across the different tight junction proteins, you can see that either singularly, these bacillus strains, or in combination, we were able to upregulate gene expression of these tight junctions. And the one thing I would mention here is that not any bacillus is going to do this. We provided these bacillus strains to this researcher at Beltsville, but those strains were chosen out of a library of over 25,000 bacillus that we have in our library to choose from. So not every bacillus and not every combination is going to work. So we do have the ability with some of these new technologies like bacillus to actually impact tight junctions. I'll show you an example of that. So with that, I'm going to show you 4 examples of, and I won't go into all of the research study, but this first one is a research study. It's a weaning and transport study done at Clemson by Nathan Long and his group in 2018. It was with beef heifers, about 7.5 months old, weighing about 500 pounds. They were sorted into pens of 4 in 9 replicates. Okay, the treatments were very straightforward. We used RFCs, or a dry Cellular product, at 18 grams per head per day, or the control was simply a corn germ carrier, as in the Cellular dry, at 18 grams a head. That was fed, those 2 treatments were fed throughout the feeding period through 69 days. Now, each pen of 4 was divided into 2 of those animals in each pen were subjected to a transportation challenge at the end of the feeding period, and 2 of the others were actually submitted to a vasopressin corticotropin releasing hormone challenge. As you can see, we took fecal samples before and after the transportation challenge. Obviously, this is a weaning study. We took body weights. We recorded feed intakes and body weight gains throughout the period. And lastly, we took serum, plasma, and fecal samples throughout the study. So one of the first things that we saw in this study was very, very interesting. And this was a microbial result. We saw that in the RFC animals, we found on those fecal samples the day after transport, we found 6% prevalence of Clostridium perfringens. Okay, Compared to the control animals, we found 56% prevalence in those control animals the day after challenge. So that is a neat effect, especially because the RFCs, the Cellular RFCs here, have no direct effect on Clostridium perfringens. This is simply demonstrating an effect on that barrier function, the killing zone, the health of that, so that these pathogens in the RFC side were not able to attach, colonize, and replicate in those RFC animals. So an indirect effect, and again, it goes back to showing you that it's not just about the bug. We can have beneficial indirect effects by managing that barrier, like Dr. Chase just showed us. Okay, one of the other really neat things that we measured in here is we looked at cortisol on these animals. Dr. Chase mentioned that that gut innate immune system is closely connected with the neuroendocrine system, okay? So we're gonna measure cortisol in these animals, and you can see throughout the 60-day feeding period here, the Stelmanax animals, or the RFCs, every 15 days we measured those. You can see the lower lines, cortisol levels were very flat compared to the control animals that were the same at the start and continued throughout the feeding period to trend upward and be statistically different. Now, the really important thing here to note is not only was there a difference, but these are clinically normal animals. This is not a disease or a clinical disease effect. There was zero morbidity in this study. So that's really significant that these changes are occurring even in animals that we can't detect from a clinical standpoint. We also measured cortisol after a transportation challenge every 4 hours. And again, you see that cortisol levels on those RFC animals are just steady. They're pegged. They don't rise during or after the transportation challenge compared to the control animals. Likewise, the other two animals we mentioned were subjected to a vasopressin challenge test, and this is measured in time here. You can see that even the RFC animals responded to the vasopressin, but they leveled off much earlier, and they came back down to normal levels much quicker than did the control animals. So again, just a demonstration of in clinically normal animals, we can manage that immune response. One of the other things we did, and Dr. Chase talked a lot about inflammatory cytokines, is on the top here, you can see that every 15 days we measured these two cytokines. And if you look when we start, those are stacked on top of each other, both the control and the RFC animals, the same as you would expect. As we go through the feeding trial, you see a difference each time through every 15 days, an impact on those cytokines. Likewise, Dr. Chase mentioned about the acute phase proteins. We measured haptoglobin as an acute phase protein produced by the liver in response to cytokines, signals, the same at the start, and a significant impact, not a difference here at 30 days, but every other of the measurements, we had a significant impact in this study on clinically normal animals throughout the feeding period on both cytokines and acute phase proteins, okay? Because of that, like we would expect from what Dr. Chase talked about, an immune response has an energy cost, okay? And one of the things, one part of that, one result of that is we were able to measure a body weight gain difference in this study, significant. Likewise, also a feed conversion difference But again, at least a portion of that we can explain with the immune response. Okay, another really interesting study here, second study, is a receiving trial also. But this time we used a combination of RFCs and bacillus. This was done by Dr. Ronaldo Cook and his group at Texas A&M. Very recently, this trial was cut short. This was supposed to be a receiving finishing trial. We got about 110 days into it, and COVID-19, the research station was shut down. But what we do have is the receiving data, and I'm going to show you that. So this is, again, Angus 270 crossbred animals weighing 575, randomized into pens of 15, 6 replicates, 90 animals per treatments. The treatments were a positive control industry standard Rumensin Thailand, RT. Second treatment, Rumensin Cellular Certilis, combination of those two technologies with Rumensin, RCC. And then just the two technologies by themselves indicated as CC. So again, I'm going to show you the data that we do have. This has not been published because this all just happened during the last month. But I'll show you some preliminary data from the 45-day receiving period. One of the things you'll first see here, and here are the treatments. CC is Cellular Certilis, Rumensin, Cellular Certilis, industry standard Rumensin Thailand. Okay, so if you look here across the first line, very, very high rate of morbidity. Okay, in all of these groups, no difference. Okay, but when we look at those animals, those morbid animals that required a second treatment, big difference here for both of these CCs, both of these technologies compared to the Rumensin Thailand. Also, when you come down to mortality, significant difference for the combination treatments, more so in this one compared to this, but again, the CC treatment compared to Rumensin, significant difference. Those were different. Lastly, the last thing we saw was total animals removed from the experiment. Big difference here between the CC and the RCCs compared to Rumensin Thailand. Okay, now I must explain that the cattle that were required a third treatment were removed from the trial. They were taken to the hospital pen and they were removed from the trial. So these numbers here of 7%, 12.9%, and 22% removed from the trial is a combination of animals that had to be treated a third time and or more dead animals, animals that actually were removed because of mortality. So big difference in removals. If you look at it graphically, this is what it looks like over the 45-day period. Again, the blue line CC, Rumensin, Cellular Certilis, Rumensin Thailand. If you can look out through here, this is that much lower, in fact, from day 22 through day 30. Significant difference between the CC group and the Rumensin Thailand group. And then later in the receiving period, again from day 30 through 45, both treatments, both CC and Rumensin Cellular Certilis were different statistically from Rumensin Thailand. Again, these technologies impacted systemically, both local and systemically, what happened to those animals in that trial. Next example is mycotoxin protection. And I'm going to show you some RFC data here. But instead of traditionally old technology, we have always measured mycotoxin binding in a test tube. What I'm going to show you here is a method of looking at cytotoxicity to bovine enterocytes grown on a cell lawn. So in a petri dish. So what they do with this method is actually incubate these bovine enterocytes with a toxin, and then after 4 hours, wash them. And then under a microscope, they look to see what % of the animals took up dye. Obviously, the more damaged cells took up more dye and were graded with a higher score. So here's what it looks like. And this work was done by Dr. Baines at Lethbridge, was reported here in 2011. What she did here with this is looked at 4 different mycotoxins and looked at the control and the 4 mycotoxins. You see a very high rate of cytotoxicity to those bovine enterocytes. And then she added a RFC product, the Cellmax or Celmax, to those mycotoxins, and you can see that they were protected. This was actually a Ag Canada project, and in addition to Celmax, her group went ahead and evaluated several products in the market to look at their efficacy. And so here's what that looked like when she evaluated all of these different products. And here we have the inverse of cytotoxicity, which is percentage of undamaged cells. And you can see right away that Celmax protected, like we just saw, Celmax protected all of those bovine enterocytes very well, regardless of the mycotoxin included. Compared to, I'll just pick a traditional mycotoxin binder. One of the things we notice here is that when we are talking about binding a mycotoxin, every mycotoxin is structurally different. That means that a specific compound is going to bind it different. So in old technology, with binders, it really left us only a couple of choices. To get activity, we had 2 choices. We can go find, if we have 2 to 3 mycotoxins present, we can go get 2 to 3 different mycotoxin binders in the ration. And the other option we have is to double or triple a dose to get some protection. Both of those options cost us money. Okay. With newer technology, we now know that we can actually protect the bovine gut barrier and the innate immune response, like Dr. Chase just showed us, with these highly bioactive RFCs. Okay, so I think the last example I'm going to show you then would be by Barry Bradford's group at KSU. And this is a transition dose titration trial on transition cows. Again, we fed RFCs at different doses, 21 days before calving and up to 40 days postpartum in this trial. And the different doses that they used of the Celmax dry product, those cows were challenged with ovalbumin to measure any kind of humoral response. And again, they measured blood for other responses that I'll show you in the next slide. So again, I'm not going to show you all of this study. There's actually a production component but I'll show you the immune component here. And when we looked at the Cellular effect, a significant response on humoral immunity by feeding these RFCs to these transition animals. Now, I would mention that this is where we, in these transition cows, this was a dose titration. The dose that we chose was actually a 2x dose, okay? And that's where we arrived at our transition dose for pre and post fresh animals. You'll notice that it's a 2x dose compared to the normal lactating dose, okay? But in those animals at the 2x, because they were under stress, we saw a significant humoral response. Not a significant response, but Dr. Chase has been talking about fecal immunoglobulins, or IgA, numerically increased, not significant. The other thing we saw down here on uterine health is significant reduction in IL-6 inflammatory cytokines measured in the uterus. Again, a systemic response by feeding highly bioactive RFCs to really have an impact not on a bug, but having an impact on that barrier and that innate immune system. So those are some examples there that I wanted to show you to really show the application of what we can do with newer technologies to impact the innate immune response. And with that, I'm going to throw it back over to Dr. Chase to really summarize what we've seen here.
All right. So what we hope to communicate to you today was, first of all, the sort of our understanding in terms of the theoretical, and then some nice applications in terms of the use of those technologies. And so I begin with this idea that what we're trying to do when it comes to the immune system is really to have this balance that we're going to have. And we know that when it's out of balance, as that little tornado that you see, there's a cytokine storm, that we see an increase in BRD, and as you saw from some of the studies that Neil just talked about, one that affected IL-6 and another one that affected cortisol, that those are hormones that are, although produced locally, they have a systemic effect. And so being able to again keep them under balance is really important. And I think, and again, those areas are being able to manage those areas is really important. I think, again, understanding that again, we're trying to keep that thing in balance in terms of homeostasis is really important. The second thing that I hope that we brought out to you and today was the fact that the immune system, it costs us, particularly inflammation, has a cost to it in terms of the productivity of the animal. So again, in the young calf, we're looking at things in terms of growth and lean, and obviously in the dairy cow, we're looking at milk, milk in the bucket or milk in the tank. And again, anytime that I take energy away and put it into an inflammatory response, there's going to be a metabolic cost to something that has to do with production and efficiency in the animal. And again, the thing that I hope that you understand from what we talked about in terms of our old thinking in terms of how we managed that barrier and how we managed with probiotics and prebiotics is the idea that it was somehow that we were tying the bug up, we were having some direct effect on the bug. Well, certainly those effects occur, and we can show those, but I think the more important thing is what it does to that barrier in terms of increasing the kill zone, and at the same time we're talking about keeping those tight junctions in much better shape. And then the other component being keeping it anti-inflammatory is all essential to really keep that dynamic barrier doing its thing again to help maximize that animal's productivity. And then one thing that I didn't spend much time on, but the bottom line is that if I can reduce colonization And so because I got more antimicrobial peptides out there, or I have an environment that's going to decrease, and obviously the amount of bugs that are going to go into the environment and therefore contaminate other animals or recontaminate animals. So again, that's just a nice effect of improving that kill zone in terms of what we can do with that. And you heard that in regards to that study that was done with perfringens. And then the other thing in terms of just looking at this whole approach, and I think this tornado sort of says it all, is the idea that we want to be prepared. We want to be proactive because we know that stresses are going to occur, that there's going to be times that animal is absolutely going to react. There are going to be multiple stresses that are going to occur. We're starting to see days like today in South Dakota, we're into the 60s, and pretty soon we'll be into the 70s or 80s to start to see heat stress. You got transportation and all those things. And so being able to, as I said in one of my last comments, was the idea about, well, we should use this during times of stress. But then the other side of that is when don't we have some types of stress? So again, thinking about how we can be proactive about that rather than being reactive, I think is important. And I think lots of times we didn't know the mechanism of some of these molecules. It was, we couldn't be strategic about it. I think now as we begin to understand more and more about that, we can be more strategic about how we can use them. And with that, we're ready for any questions and that are there from the audience.
Thank you, Dr. Chase and Dr. Neil Michael. If anybody has any questions, on the right hand of your screen under the audio controls, you can enter in those questions if you haven't found that yet. We've got a few questions on the floor. Dr. Chase, in regards to the calf, is a calf born with an effective mucus layer?
So that's a good question, and the thing that really so the bottom line is all the pieces are there. In other words, they're producing antimicrobial peptides. Probably in terms of mucus formation, there's probably some mechanical stimulation that's involved for part of that. But I tell you the other huge part of that is hydration. I mean, so if those calves are adequately hydrated, the mucus function should be there, but again, it will take off in regards to that. But in terms of those epithelial cells producing antimicrobial peptides, that's certainly their IgA will be a little bit later because there's just a matter of that animal's got to be immune stimulated, and that's really where colostrum management is really important because colostrum will help in terms of the colonization of that gut, and which then will directly affect how fast that immune response comes on in that calf. So colostrum management isn't just about antibodies, but it's actually about managing microbiome as well. And they've shown that you can see anywhere from 2 to 3 logs less colonization when you don't feed colostrum.
Okay, and how about antimicrobial peptides? Are they specific to non-native flora, or can they be upregulated to a point that is detrimental to a native flora?
So that's a really good question. I think what's I think's come out of that from most of the work that's been done. So for one thing, I'll be very honest with you, to actually do the assays to say what's being produced, pretty much everything that we looked at is not actually isolating the protein itself, but rather looking at message. But there are some that, for example, there's groups that are specific for gram negative and more for Enterobacter, which I think we would agree that probably that's going to be more of a group of pathogens. I think you see against lactobacillus and Bacteroides and those things that in some of the other bacteria that we would say are in the what we look at the commensals, that those antimicrobial peptides those are either less likely to be susceptible, or the specific antimicrobial peptide isn't produced against those. But that's a good question because again, the problem that we have, it's not so much that you can take a gut contents and titrate it against like you can say for antibodies, and titrate it and say, okay, here, this is what we got, and what's it going to do? It's all based on taking those proteins and expressing them, and then measuring that, and then trying to translate that back to what's in the gut. So it's a good question that I don't have the perfect answer for, but I think in general, a lot of them are directed against particularly the gram negatives, which I think, obviously is Enterobacter more in the pathogen group.
This question is for Dr. Neil Michael. In the receiving study, is there any comment on the difference in bloat incidence between the three groups?
Sure. Like I said, I didn't have time to go through all of that, but one of the, if you'll notice that in that slide, we started seeing some bloat in those animals without rumensin. The diet that was being fed, that receiving diet, had a couple different ingredients that were very, from a bloat standpoint, promoted that. And without the rumensin in there, we know that rumensin can have an impact on that occurrence. So that was right. That all occurred as those animals got up to intake right at the 45-day period, and we switched those from that receiving diet to the first part of the finishing diet, and that bloat incidence that reduced immediately after we got off of those ingredients. So good observation. I didn't mention that, but it happened right at the end of the 45-day period. Yes.
Any comment as a follow-up how RFCs and bacillus would help prevent bloat?
Specifically not from a bloat standpoint. Obviously, the RFCs, remember, we do, Salmonex is a combination of yeast culture plus the RFC. So from a rumen impact and digestion, intakes, rumen stability, the yeast culture is in the Salmonex is going to help us there. From a biology standpoint, again, we're not replacing the ionophore from that standpoint.
Okay, we've got one for Dr. Chase. Do viral infections stimulate the amount of neutrophil response that bacterial infections do?
So, that's a good question. Some of the viruses that really stimulate IL-1 can do that, but typically we think that that gram negatives in particular have a tendency to stimulate more. But there hasn't been what I would certainly call a lot of head-to-head between viruses and bacteria. Typically what people have done is they've looked at different groups of bacteria, but I haven't seen where they put that straight up against a virus to see exactly how they behave. But we certainly know, and I can tell you, for example, BVD, we have certain strains of BVD that do a tremendous job, and this being negative, in terms of stimulating macrophages, where they actually don't kill the macrophage, they live in the macrophage, and the macrophage will stimulate more pro-inflammatory cytokines. And then there's another strain, it's another BVD strain that doesn't do anything at all with that. So there's a strain effect, but in a head-to-head, I would probably still sort of lean more times than not that that particularly gram negatives would probably be a little stronger than inducing it. But again, I don't have the data that kind of in a head-to-head.
Dr. Chase, would you recommend using an NSAID along with antibiotics to treat BRD in young calves and heifers?
Well, I think using non-steroidals. I definitely think there's a place for those in terms of being able to knock that inflammation down. But the problem with them is they're always they're more effective when you can get it into the animal before inflammation starts. And so that's always one of the issues is that you're a little bit behind the 8 ball. But I in general I like using NSAIDs. The other thing is that NSAIDs, unlike if you use dexamethasone or corticosteroid, is that they don't have an effect on lymphocytes where dexamethasone really knocks out lymphocytes, and I think that really and can cause a deficit in some animals where NSAIDs don't have that effect, and they really don't have an effect on vaccine response. I mean, they have they have an effect on inflammation, but it doesn't seem to affect that part of the inflammatory response that's necessary to develop a good immune response.
Okay, I think I'll ask one more question and we'll probably close it up. But thanks everyone for attending. The last question is, do RFCs have a positive effect on removing E. coli or Salmonella after they have already attached to the gut lining? Or are they only effective in agglutinating these organisms before the attachment to the epithelial surface?
Yeah, so great question. So once those are attached, again, they're using the type 1 pili to attach. They do that to colonize and continue to reproduce. Once they're attached, we can't agglutinate those. We can't remove them from the surface. What we can do is, as they colonize and start to reproduce, we can agglutinate any of those new bacteria so that they don't colonize, and overall we can prevent that. Even on it where there has been some colonization, we can slow down that logarithmic growth and possibly prevent a huge outgrowth at that point. So that's kind of a timing thing, but yes, there's again, I think we need to think about not the fact that, one bacteria or 10 bacteria colonize. What really causes disease is these huge outgrowths, these logarithmic growths. And if we, together with agglutination with the RFCs, together with the health of the mucin layer and everything else we've talked about here, they're all pieces to the puzzle. But again, the fact it's not about the individual bug, it is about slowing the process down and managing the immune response. Good question. So with that, yes, we went long on time, but again, I really want to thank everybody for joining us today in this discussion. Feel free to follow up with your Arm & Hammer account manager, tech service person, to look at any of these examples further. We'd be happy to go into more detail on those, especially on the most recent one I showed you. Once we get that analyzed and that becomes published, we can go deeper into those, into that data. But feel free to contact your Arm & Hammer person. Also for the CE credits, and like I said, you should be receiving a link as a follow-up early next week with the recorded portion of this webinar. With that, thanks again. Thanks, Dr. Chase. Thanks all of you, and have a good and safe day.